Well, thank you all for showing up. It's exciting to see so many people that are interested in a hobby I've loved for literal decades. So of course we're here to talk about celestial navigation, the history and the methods of navigating by the stars. When we talk about that, it's important to, well, there it is. Navigation by observation of the positions of celestial bodies is the definition according to Merriam-Webster. But when talking about celestial navigation, it's good to first talk about navigation, which navigation is the art and science of determining the position of a ship, plane, or other vehicle and guiding it to a specific destination. Before we got to all these fancy methods of doing it now with GPS and even celestial navigation, the most simple and still very commonly done version of navigation is dead reckoning. It's the act of estimating your current position using the direction and distance traveled from a previously known position. So you know where you're at, you know the direction you're heading, you know how fast you're going and how far you go, and you get to some place and you have what's called an assumed position. Assumed because you might not be totally accurate. Your direction might be a little bit off, you might not know your speed precisely, but you're probably pretty close, so you have an assumed position. So when people first started traveling a lot and going out on the sea and stuff, this was pretty much totally how they navigated. Was they would just do dead reckoning. They knew where they were going, they knew a direction they were heading, they hopefully got where they were aiming at. Now you notice we talked about the direction in that previous one. It was actually said the bearing, 74 degrees. So what we refer to for the bearing is on the compass, we go around from clockwise, starting with 0 being at north, 360 degrees around. So you can see like 74 degrees, you'd be kind of angling off that way. So when we talk about a bearing, we always talk about just the degrees. We don't worry about saying north or west or anything like that. And the compass rose, you'll always see that sort of on your map to help you know your orientation on the map. So the earliest forms of celestial navigation was dead reckoning. And they were using the stars as their compass. They knew a particular star would appear in the sky in a particular direction depending on the season or the time of day, and they could use that to find their way. Earliest people known to have done that kind of thing were the Polynesians, the Polynesian Wayfinding we're going to talk a bit about. Mayans were known for doing some amazing astronomy, and they were thought to have also used the stars for navigating. And of course the Vikings famously sailed great distances and had some of the earliest navigation tools. So we'll talk about those. I particularly like talking about the Polynesians because they are amazing. They were amazing sailors. The Polynesian tradition of navigation can be traced back as far as 3000 BC, so farther than any other culture that we know of. It incorporates a variety of techniques. They could look at wave swells, and based on how the currents are flowing past islands, could tell if an island was in a particular direction, even if you couldn't see it. They knew that birds migrated to certain islands, so they would follow the tracks of birds. They looked at clouds and the sky and could see how the colors would be different based on if there was a distant island that you couldn't see the island, but you could tell where it probably was based on what the sky looked like. And they could even put their ear into the water and hear the sound of waves crashing against distant rocks. None of that, of course, is celestial navigation, but I think it's really cool, so it bears mentioning. But they also had what they called the star compass, or what we call a star compass. And so they actually did know their constellations, and they knew the stars, and they would use that to navigate. If you've ever watched the movie Moana, and there's a scene where she holds her hand up to the stars, that's literally what she's doing. The Tupol and Tan is basically just west and east. And those all stand for particular stars or constellations. This was all an oral tradition. They didn't actually use charts or maps. They would learn this. They'd lay something out like this on the ground and teach it to new sailors. So it was amazing the extent to which they had this great, rich navigation history and talent that was passed down almost entirely via oral tradition and a few things that they would actually not take on the boats with them. They would maybe carve things and keep that as just to maintain the tradition.
Is this still being done?
Yes, it was in danger of dying out at one point when Western cultures had moved into the areas of the Polynesians, but there were some people that actively decided to keep it alive, and there was actually some famous voyages in which to prove the fact that they could do this, they said, okay, we're going to go on our dugout canoe outriggers and sail several thousand miles to this island and then make it back. And then like, well, that could be a fluke. And then they did it again, and they proved that, yes, we actually can navigate like this. And there is now a Polynesian Naval College that actually keeps these traditions alive. So that's very good. And I have somewhere a link. After all this, I'll send out some of the links that I used for researching this class. And if any people want to sign up with an email address, I can make sure I mail out some further reading that I think you people will find very interesting.
So how would you actually use this?
Well, I don't know the full process, but like I said, each of these refers to, say, like a star or a constellation that they would recognize. It would be different than ones we probably are used to. They'd have their own names for it.
You have that mental picture in your mind.
Right, they'd have a mental picture, and it follows just right around around the sky, and they would have to adjust for the seasons and for the time of day, because of course the stars kind of track across the sky. So there is, a process by which they know, okay, this particular one I'm going to have to adjust a little bit based on this particular time of year and so on. So Polynesians really got around. They colonized what we call the Polynesian Triangle, which you can see goes all the way from Hawaii down to New Zealand and over to Easter Island. So that's thousands of miles in the Pacific. So very impressive feat. The Mayans, though, also did some impressive things. They didn't get quite as far, but the Mayan astronomy in many ways actually surpassed Europe of the time. Ptolemy was kind of the big astronomer in European cultures, and he actually got some stuff not as accurate as what we found in the carvings in various Mayan temples and things like that. They used it to predict the equinox, solstice, eclipses, and the appearance of Venus. And they divided the heavens into 8 partitions aligned with the cardinal compass points. See that in a moment. And that allowed the seafaring Chontal Maya to navigate on long ocean voyages. The Chontal Maya were kind of in the very southern end of Mexico, and they went across the Gulf of Mexico into the Caribbean and even as far as Florida, we believe. So still a pretty significant ocean voyage. And they undoubtedly used their knowledge of celestial bodies to do that. So you can see they've got this sort of various compass points. They assigned a Mayan god to each of the compass points. Interesting thing, north is actually off to the side instead of up above. So kind of an arbitrary decision on our point to treat north as the top of the map. And this Madrid Codex, there's actually all these little interesting markings that they haven't completely decoded. They think this might be astronomical predictions, of like they were actually able to predict when certain celestial bodies would be in particular positions in the sky. So they were pretty accomplished astronomers. The Vikings, though, are ones that are known for some of the earliest navigation tools. They sailed between, of course, Europe and Greenland and as far west as North America. And you see, again, of course, they've got their compass points with their various symbols to be the different cardinal directions. But the interesting thing that they did is the sun compass. It's essentially like a sundial, but it tells direction instead of time. And does that by you rotate it, and when the shadow of the gnomon, the little post in the center, when that falls right on top of a groove that you have in there, you know you've aligned it with north. And we also now think that they also might have used it to determine latitude. Now, they wouldn't have referred to it in the same way as us, but they would know how far north or south they went based on, if that shadow is going a little farther or closer depending on the season, they can actually line that up. And actually, you can see that if we go to a more modern version of the sun compass, you can see you could adjust it based on the season, and it's got different grooves for the different latitudes. So you can actually kind of use it in a couple of different ways. Another thing that they're known for is the Viking sunstone, which for a long time was believed to just be sort of a mythical thing, but as we've found more writings on it, we believe that it was actually a thing they used, was possibly quarterite or Iceland spar, which is a crystal that polarizes the light in such a way that even if you have very dim light, because the sun has gone down already, or maybe there's clouds, the polarization lets you actually zero in exactly where the direction of the sun is. So even if they couldn't get that nice clear shadow, they could still determine the direction of the sun, and that would help them navigate. Now, of course, we talked about stars being used as a compass. As many of you probably know, Polaris is a pretty key star that navigators, at least in the northern hemisphere, have used because we call it the northern pole star. So the nice thing about that is no matter where you're at, if you can see Polaris, you know where north is. In particular, what we call true north, which is the actual geographic north pole where the axis of rotation of the Earth is. That's actually different than the magnetic north. So that's actually a thing as a navigator you need to be aware of, is that your compass isn't necessarily telling you where true north is. And when we navigate, we always use true north. We use magnetic north, but we adjust it to true north. And we'll talk a little bit more about why that is. So on maps, we talked about that compass rose earlier. There's actually a thing that'll always tell you something called the magnetic declination of how much your magnetic north in that area, that region, will vary from true north. So a little aside there. But Polaris is, obviously has been probably the most useful navigation star in the northern hemisphere. And we use that with the latitude longitude system, which was started to be developed pretty early on, kind of came into its day with a lot of the European era of navigation and exploration. A little refresher for those of us that haven't looked at a globe in a while. Of course, you have the longitude lines go from pole to pole. The latitude lines go across, with the equator being sort of the middle of that, and they go from 0 to 90 north latitudes and 0 to 90 south latitudes, and then you get 0 to 180 west and 0 to 180 east longitudes. It makes a nice kind of grid system for us to determine exactly where we're at. And there's actually, with celestial navigation, this system actually grew out of celestial navigation because the angles to the stars can be used to kind of translate to those angles. These are actually angles from the center of the Earth. You can think of any of these degrees. That's why latitude and longitude is in degrees. It's because we're talking about if you took a line from the very center of the Earth and drew it out to one of these points, it's sweeping out an angle. So like, if you go from the 0 prime meridian out to this 40-degree line of longitude, you can think of there's like an angle from the center of the Earth going from the prime meridian to this point here, and that angle from the center is 40 degrees. So literally any latitude, longitude position on the surface of the Earth, it can be thought of as an angle from the center of the Earth. So finding our latitude, we can find our latitude using Polaris because of that whole angle thing. Now, Polaris, being a star, is very, very far away, very large and very far away, and so the light from it arrives parallel no matter where you are on the Earth. It's that kind of whole thing when you're driving in your car and you look out and you see a distant mountain or the moon or something like that, and it seems to be tracking with you. That's because it has what we call no parallax effect. It's so far away that no matter where you're at, the light's coming from the same direction. So that's very useful when it comes to navigating, because as you move over the curvature of the Earth, the angle of Polaris is going to change only because your orientation to it is changing. Whereas if it was something much closer, it would change just because of perspective. And as a result, if you see Polaris directly overhead, you know that you're right at the north geographic pole. So it's at 90 degrees from our horizontal. As you move down to lower latitudes, closer to the equator, it will appear to drop in the sky. So if you see Polaris at 45 degrees, you know you're at 45 degrees latitude. You're halfway from the pole down to the equator. Similarly, you get down to where it's like right at the horizon, you know that you must be on the equator because you're seeing Polaris right at your horizontal. So that's just a kind of a nice convenient thing that we have this star that happens to be right. It's actually slightly off from the center of rotation, but it's very close to the center of rotation, close to that point right above the North Pole where the axis of rotation of the Earth is. They have a little more work to do. They use something called the Southern Cross, which is not at the center of rotation, but it points to it. So you have some stars, and the couple of the stars in the Southern Cross point toward the center of rotation, and the distance to that is like a couple of, you measure that distance between the stars and you go 2 more lengths, I think it is, and then that gets you to that center of rotation, and then, so you can kind of determine it that way. So yeah, we're kind of spoiled here in the Northern Hemisphere that we have Polaris we can look at. Okay, so one of the earlier navigation things for doing that measurement of the angles is something called the astrolabe. It's an ancient astronomy tool. It originated in the Middle East. It was kind of a mechanical calculator. It could solve various astronomical problems. A lot of them, they have these like dials you could put on these little discs, and you could rotate them, and you could even predict like lunar phases and various other astronomical things. But one of the things they did is they have an inclinometer. They have this little thing here that you can kind of tilt, and you hang this thing so that it'll hang vertical, kind of like a plumb bob. And then you move that little diagonal bit until when you're sighting along it, you're looking right at the star you want to get an angle on. And then you can read the angle reading off that edge. And then that'll give you that angle, like if you were looking at Polaris, it would give you that angle above the horizontal, and then you'd know your latitude. Now, the downside of that is you're moving around on a boat. It might be hard to get it to stay stable. But in general, it still was a useful navigation tool. A different tool that does something similar is called the cross staff. This was more popular in European cultures. And it kind of solved that stability issue by the fact that you sort of lined it up with the horizon. So even if you're on a boat moving around, the horizon was this nice stable point you could aim at. And then by sliding that little crossbar, it would change the angle between the top and the bottom. The bottom of the crossbar would be at the horizon. The top would be at whatever star you were trying to aim at, or the sun or whatever. And then based on where you'd slid it, you'd have some marks that would tell you how big of an angle you've made. And so it's basically another way of getting the same thing. You're getting that elevation angle above the horizontal. But what we're really interested in is the sextant. And it has the advantage of it does sort of the same thing in that you're viewing an angle based off of the horizon. So you've got that stability thing kind of like, but it can get more accurate because it has this micrometer dial here. And I'll show you that. We'll get a chance to look at that a little bit more, where you can dial in little fractions of a degree. And it's got a little telescope so you can see things a little more, a little more detail. They started to be, I think, came around a little more than 2 centuries ago. And so that really kind of got to where we could get some really accurate navigation, particularly as the actual process of celestial navigation began to evolve and have newer techniques. Well, we talked about how we could get latitude. And you can get latitude, like, say, from the northern pole star, or I talked about from the sun. Based on the season and a little bit of calculation, you can know how high the sun should rise where you're at. Based on that, you can get latitude from the sun as well. But longitude is a little trickier. And the reason is we're looking at these celestial bodies above us. They're moving, they're arcing across the sky because the Earth is rotating. So they're kind of fixed up there in the heavens. Earth rotates. As a result, the stuff we're looking at in the sky tracks across the sky. As they change the position in the sky, it's the same as you're moving east to west. I call this, is it later in the day or am I farther east? So like if I see a star, like say nearly directly overhead, and I know that star and I know where, based on looking in something like a nautical almanac, I know where I must be based on that. The problem is, if I don't know the time, it could be that I'm actually 15, let me say it this way. The stars move basically 15 degrees per hour as the Earth rotates over a 24-hour period. So what I'm seeing in the sky right now, someone who's 15 degrees west of me will see the exact same sky an hour later. So if I don't know what time it is, I can't know if I'm 15 degrees east or west, if I don't actually have accurate time. So I don't know, was that clear? Okay. Yeah, there we go. Okay. And this can lead to some serious problems if you don't actually know your longitude. There's something called the Scilly naval disaster at 1707. It was on October 22nd, 1707. 4 British naval ships were grounded and sunk off the coast of the Scilly Isles. Over 2,000 sailors, including the fleet commander, Sir Cloudesley Shovel, lost their lives. And the tragedy was attributed to inaccurate navigation and remains the most deadly naval disaster in British history. And it led to the British Parliament passing the Longitude Act in 1714. It established a 20,000-pound prize for developing a practical way of determining longitude at sea. I like to think of this as the first X Prize. Like now they have these prizes of like, commercial space flight and various things like that where they put up big prizes. This was kind of that sort of thing. Like if you can solve the longitude problem, we're going to give you this big bunch of money. 20,000 pounds was a lot of money back then. This encouraged John Harrison, a British carpenter and clockmaker, to try and invent the first functioning sea clock. And while Harrison was eventually successful due to politics and rivalries on the longitude board, he was not awarded the prize until many years later. So he knew that to figure out your longitude when at sea, you needed to know the time, because then you could look things up in astronomical tables, but if you didn't know the time, you might be farther east or west than you thought you were. There's actually a very fascinating documentary called Longitude. It's sort of a bit of a docudrama kind of thing. I think it's on Amazon Prime, but it covers his quest to make the first nautical clock, and I recommend it. Here's some of his early ones. They were monstrous things. They did take these things out of boats. They did have some issues with how the motions of the boat affect them that he was trying to counter. But eventually what finally like the problem is he partnered with watchmaker John Jeffries, and he built a custom watch incorporating the innovations he learned from his sea clocks. And it was successfully tested on a round-trip journey from England to Kingston, Jamaica in 1761. So you can see this was quite a while after the initial contest was put out there. And despite this, sorry.
Was that the first spring-wound watch?
I think there were other spring-wound watches before that, but they still had, they would lose or gain time. They needed to like have something that had could keep time very predictably. And so they actually came up with some techniques. I don't know the mechanics of it, but he came up with some techniques that made this particular watch keep time much more accurately than some of the watches that were before it. Despite his success, the longitude board questioned its practicality, preferring lunar observations. So the longitude board was stacked with a bunch of people from the Royal Society and a bunch of the scientists, and a lot of them were astronomers and really preferred just using pure astronomy to try and lick the problem. And there was complicated ways you could use lunar observations to kind of get to the same thing, to know what the time was, but and honestly, it was not as easy as just using a watch. Now we're going to talk about the sextant. So that's the tool that's most popular for doing celestial navigation for the last 2 centuries. This is actually I've got some pages right from my manual that came with my Davis Mark 15. This is a fun little plastic sextant. You can pick these up for under $200. Some of the more heavy-duty professional ones you can spend hundreds to several $1,000s depending on what kind of sextant you want to buy. But this is a fairly inexpensive one that still works pretty well. This is actually a gift from my wife because I was lamenting that I couldn't find where this one was stored. She got tired of me complaining about it, so she bought it for me for Christmas. Which is nice because it's so lightweight and easy to carry around that I've managed to take it on some trips with me that I otherwise wouldn't be able to. And we got to do a little bit of sailing about in the Baltic, in the North Sea last year, where I got to take some sextant sights, and so that was cool. The parts of the sextant, you can see that it's got this little quick release thing here where you can move this arm about. It's got that, and the index arm is the part that scrolls. You see it's got degree readings along on here. And then it's got this thing called a micrometer drum that gives you, it moves it just a tiny bit and you can get more precise measurements. And the way you get your angle measurement is you've got these pair of mirrors on here. You see on there they call it a horizon mirror, this one here, and the index mirror is this one here. The horizon mirror is you have a little telescope and you look through it and you line it up with the horizon and you move this arm here, you see it's got a half silvered mirror. So half of your view is what you're seeing straight ahead of the horizon, the other half is what's reflected off this mirror, and you can change the angle that you're viewing on that index mirror by moving this arm around, and then little small movements you can fine tune it. It's got some little solar shades in case you're looking at the sun that's very bright. You want to make sure you don't hurt your eyes. And then all you really do is you line up until the thing you're viewing, the angle you want to get, like it's the sun, you move this arm until it seems to come down and touch the horizon. And when you've got that touching the horizon, then you can read the angle off this bit here, and you know what the difference is between the horizon and the body that you're viewing, whether it's the sun, moon, or a star. We'll get into more detail. There's a few other steps involved, but that gives you the basics of the parts and how they're used. Back over here. This actually is going to kind of run through some of what I just said. It kind of shows you what you see in the eyepiece, where you bring that down, and then it's going to show that you rock the thing back and forth, and that's just so that you make sure you've lined it up vertically. As you rock it back and forth, it will, when it's at its lowest point, you know that whatever you're viewing, if it's at its lowest point, you know that you've got it vertically at that point. So that's kind of what you see through the scope of your sextant. We will actually be taking some sun sites like this in the 201 class in the spring. When we read the number off, I mentioned that there's that degree reading thing there, and then you would have this micrometer drum here. You basically get sort of to the closest degree on that bit there, and then you fine tune, you turn that knob until the thing you're viewing is right there at the horizon. And then when you read it, you can see that that's degrees along there, and these are what we call arc minutes. There's 60 arc minutes per degree. So it's 1/60th, each of these marks on there is 1/60th of a degree. And we can actually get a little closer than that, because if you can see these little 5 lines here, what you want to do is take that top line, and you're getting that, whatever number it's closest to is the arc minute, and then you look at what is the next line that is dead even with it. And that tells you how many, it's basically each of these little 5 marks is 1/5 of an arc minute. So if I count down to where this one here is lined up with this mark here, I know that that's 2/5. So it says here that this reading is 45 degrees, 16.4 arc minutes. So as you look over the degrees, it's just past the 45 mark. Over here, the very top line is just below 16. So we know that we're a little bit past 16, but then we count down 2 more lines, and that one is in line. Those 2 are dead even, so we know that we're 2/5 of a arc minute beyond that 16 mark. So it's a little bit of a kind of a funky thing to get used to, but you can basically, using these actually I think it's 6 lines here, you can get to a 1/5 of the arc minute accuracy. I think I'm saying 2/5. I meant to say it's 2/10, 1/5, whatever. And we can use that to do something called a meridian passage sun sight. We got a few different types of celestial navigation fix. So this is, at this point, I should make clear, we've moved beyond dead reckoning, where we're just sort of estimating where we're at based on the direction we're heading. Now we want to use the stars to say this is the actual place on the surface of the Earth that we are. And I like to think of it as, we call it a fix, because we're fixing that error that we have from our dead reckoning. We're actually zeroing in to know more precisely where we're at. And there's a couple different main types of celestial navigation fix we can do. There's what we call the solar noon fix, or the meridian passage sun sight, which is when we're looking for that moment when the sun is at its highest point. And that can tell us our latitude and longitude. There's the other type that I'm going to also talk about is star sights, where during nautical twilight, right when the sun is setting or when it's rising, you can get sights on multiple stars, sometimes the moon, and you can use that to also get a celestial navigation fix. I actually find those a lot of fun, and they're actually technically a little more accurate. But right now we're going to talk about the meridian passage sun sight. And basically at any given moment, there's one location on the surface of the Earth where the sun will be directly overhead. And this is the sun's geographic position, or often called ground position. For short, we call it the GP. This is actually true of any celestial body. At any given point, anything you see in the sky, there will be one point on the Earth where that thing can be seen directly overhead. And that's a key concept we use whenever we navigate. We're finding our location relative to the ground position of some celestial body. The GP of the sun can be looked up in a nautical almanac for that year, as can a variety of other celestial bodies. At the moment of the meridian passage, the sun's GP will be at the same longitude as you. So looking over at this globe here briefly, if I'm over here on this point on the globe and it's rotating, and the sun is out here off in space, there'll be a point in which the sun kind of is lining up so that it's right in line with me. That will also be the time when the sun is at its highest point in the sky. So we can identify that moment when the sun is at its highest point. We can know what our longitude is. So yeah, at the moment of the meridian passage, the sun's GP will have the same longitude as you. And the angle of the sun at that moment tells how far north or south you are from the sun's GP, and thus what your latitude is. So we can get both our longitude and latitude from capturing that moment when the sun is at its highest point. The actual process kind of goes like this. You take your first sextant reading at least a half hour before estimated local noon. You know roughly where you're at because you've been doing your dead reckoning, but you don't know exactly. But you know about when noon should be. So you start a little ahead of time just to give yourself some room for error. And also you want to be catching the sun while it's rising, while it's still on its way up. So you start taking sextant readings and you start noting the angle you're getting. And you note the time. It's very important to note the time. You take a reading every few minutes until the altitude angle, that's what we call the angle above the horizon, is the altitude angle, until it begins to decrease. The highest angle that you measured can be used to compute your latitude. So you know how high the sun got, so that'll help you determine what your latitude was. The tricky thing is that as it gets to the top of that arc, it's going to seem like it's staying at that same height for a little while. So you don't know where exactly that highest point is, because it's really, you know how a curve goes. It sort of like flattens out right at the top of it. So we view the sun with our sextant, and we wait for that exact moment it appears to touch. Where am I? Oh, okay. Set your sextant to the exact angle. I almost skipped a step. Set your sextant to the exact angle of your first reading when you first did it. And then you keep taking readings and you view the sun with your sextant and wait for the exact moment it appears to touch the horizon in this telescope, and you note that time. So what you're doing is you're basically waiting for that moment when the sun has started to go down on its arc and has reached the exact same altitude angle, the exact same height over the horizon as when you first took your first reading. And then you can take the average of those two times, the first and your last sextant sight. And the average of those gives you the middle of that arc, and it gives you your solar noon. So you can use that to compute your longitude. You know exactly at what time the sun was at that highest point by taking the average between those two first and last readings in which you had this exact same height of the sun. So does that make sense? I probably should have made a diagram to help show that one. But
So during the day, the only time you can take it is at noon?
Yeah, you start a little before noon, you take your readings, and then you go a little bit longer, the same amount of time after. And so you basically have three key times you can do celestial navigation. Nautical twilight close to sunrise, close to sunset, and solar noon. So technically there's some occasions where you can do, if you have the sun and the moon up at the same time, you can do what's called a two-body fix off the two of them. But unfortunately that only happens maybe you're 1 week out of every month. So anyway.
How do you know when estimated local noon is that in the book?
Yeah, that's in the nautical almanac. It's the kind of thing where you know roughly where you're at, so you know, okay, I'm not sure exactly what my longitude is, but I know it's within this range, and therefore noon is going to be close to this particular time. And so you start early enough that depending on how off you are, you're still going to capture it. So. Okay, so using a sextant. I'm actually going to play another video and I'm going to talk over it. The sound on this one. You see here, I'm getting the sextant out, and the first thing I'm doing is calibrating it. And the way you calibrate it is you put it at the 0 position. So you put it at the 0 position and then you sight on the horizon. And if it's all perfectly calibrated, when you look, you should see the horizon in both the mirror and in the clear spot. They should be lining up because you set it to 0, so the index mirror should be saying the same thing as the horizon mirror. If it's not, you've got a couple little screws you can adjust. And that actually changes the tilt of this mirror a little bit to put it back into calibration. Then when you get to the point you've got it calibrated, and you want to actually do your sun sight, it's really important to put some solar shields down. So that's what you saw me doing, is flipping some shields down. I usually start with putting all of them down and then flip them up because it's better you don't want to go the other way and not have enough shields when you start. I usually put one down on the horizon because the light reflecting, the water right below the horizon, or right below the sun is going to be reflecting with the sunlight, so that can be a little bit bright as well. But that's really an important step. Is if you're doing a sun sight, you've got to use the solar shields, otherwise you can hurt your eyes. Because you are looking at a little telescope, you know. So then what I'm doing is you see right there, I'm taking a little clicker there. That's me getting the time. I'm actually going to pause it right there. So anytime you do any of this, you got to know the time. Like we're talking about, that's the key to the longitude problem, is that lets you look up in the nautical almanac, get the right ground position for the celestial body based on that time, and then allows you to determine longitude. Now you notice there it says sun lower limb. That's a nautical term for basically just the lower edge of the sun. We're measuring the sun, and when the lower edge of it is hitting the horizon, that's when we're taking our reading. You can do it from the upper. They call it upper limb, of course. It's more common with the moon to like sometimes do upper limb instead of lower lower limb, because of course the moon will not always be full, and you might not get a nice perfect lower edge, so you might do it from the top. In the nautical almanacs, all the readings for the positions are based on the center of the sun or the moon, and therefore you have to subtract or add what we call the semi-diameter, basically just half the diameter. And they got the tables, all the tables that help you with that. So that's the only reason why we have lower limb there. And then you can see that I've got that reading there. And again, you can kind of see, follows that rule. We're just before 40, so it's 39 degrees. We're a little bit below the 40 arc minutes, and you have to count down like 4 pips to where that fourth one is lined up perfectly. So that's 2/10, 1/5 times 4, 0.8. I can do math. So that's basically, how you get that reading. And you notice I had this little clicker here. Normally people would use something like a little stopwatch or a nautical watch that keeps time. I've got the little innovation. I've got one of these Bluetooth things that you use for clicking camera shutter, and it basically, my phone then will record the time for me when I click that. I find that very easy, a lot easier to hold this when I'm doing it rather than trying to hold a full watch or something. Really what's a nice way to do is if you have someone helping you, you just say mark, and the other person marks the time for you. When we do the class in the spring, that's what we're going to do, is we're going to be in pairs, and that'll make it a lot easier. You notice it's in GMT time. All of the stuff in the nautical almanac is in Greenwich Mean Time, because we're doing everything based off of the prime meridian. They wouldn't want to make a different almanac for every single time zone. So you always take your local ship time and convert to GMT when you go into the almanac and look stuff up. I personally just find that I set my watch to GMT so I don't have to make a conversion later. Go back to this.
That would make a difference where you are. If you're on the boat, what if you're about to die?
It does make a difference, and we're going to get to that. That is an actual very good question. So we will get to that in just a little while. Let's back up here. Okay. I talked also about nautical twilight. And nautical twilight is basically the sort of magical time in which the sun has gone down or not yet risen. So the sky is still dark enough to see some of the brightest stars. We have like several dozen navigation stars. They're the ones you know from the constellations. But we also need it to be bright enough that we can see the horizon. So there's this time right before or just after sunset or sunrise where you have both. You can see the stars, you can also see the horizon, and it usually lasts about 45 minutes. And that's when you can take star sights. And I've got a video of me taking some star sights.
It's nautical twilight, and I'm taking 3 sextant sights. The first is Saturn, and I managed to find it pretty quickly, since it is very bright and relatively low. Saturn was at 24 degrees and 7 arc minutes. Next is Sharpitor, and this one takes a bit longer, mostly because I'm initially holding the timer button incorrectly. By the time I sort that out, the star has moved on from the horizon, so I have to adjust the micrometer drum again. I log Shedar at 39 degrees, 36.2 arc minutes. The last star is Altair, and I'm in a race against time as the light fades and the horizon becomes harder to see. It's a lot higher in the sky, which can make estimating where to start the index arm more challenging. But I eventually find Altair at 55 degrees, 33.8 arc minutes. That gives me 3 sextant sites to work with, enough to plot some lines of position and determine where we are.
Okay, so here were those values we got, we took with the sextant there. That was the date that we did it with just last year. We have something called index error. Index error is basically just a mechanical error in your device. You know that when I'm thinking and getting a particular angle reading, it's actually maybe 4 arc minutes higher than that. And that's just the way this sextant is. Generally, you can get rid of that with calibration. On older sextants, sometimes there was a permanent index error that you couldn't get rid of. And you had to note that and then always subtract it. What's kind of handy is if you're in a real hurry to catch your sextant sites and you haven't had time to calibrate, you can go ahead and take your sites, then calibrate afterwards and note how much you had to correct it. And then add your index error into the numbers you took. So sometimes I still end up doing index error if I'm in a hurry and I haven't calibrated. So I calibrate after the fact and then add in whatever my change was. But then you have this eye height. We mentioned, like, does it matter how high you are? It absolutely does, and we'll talk about why that is. We're going to use the star Altair as our example. It's a nice bright star in the summer triangle, so it's an easy one to pick out. Altair, Deneb, and Vega are ones you use a lot. I find myself sighting on Vega a lot. It's one that's visible, quite bright and quite visible for much of the year. We have to apply corrections. So it's all those little things that can cause error that we have to adjust for. We start out with our raw sextant reading, that HS, the S is for sextant, H for height. So we have our raw 55 degrees, 33.8 arc minutes is our altitude angle. And then we have the IC is the index correction. In this case, I had calibrated my sextant, so it was 0. But then we have dip, where your eye height comes into it. And the reason is, as you're up the Earth having some curve, the higher you are, the lower the horizon is. It may look like it's straight out ahead, but it actually dips a tiny bit. And the higher you go, the more it'll dip. It's only on the matter of arc minutes, a little fraction of a degree, but it's enough that it'll affect the answer that you get if you don't account for it. And we have a formula that gives you that approximate change. So if you're working in feet, it's 0.97 times the square root of the height of eye in feet. If you're doing metric, it's 1.76 times the height of eye in meters. Since we're not in Europe, I'm going to be using feet. So anyway, actually in this case, I guess I actually used meters. I like it. So yeah, I was at 2 meters. And this is actually a page from the nautical almanac. So you don't have to do the calculation yourself. They very conveniently pre-calculated a bunch of the answers for you in the nautical tables. Because of course, when this all was first invented, we didn't have calculators. So they pre-calculated all these things in tables to make it easy for the sailors that were out at sea. So you can just go down the column and find the number of meters, and you can find the matching number. And that's the number of arc minutes, 2.5 arc minutes, that you subtract from your angle reading, essentially taking that little dip angle and lifting it up to horizontal. So we subtract the 2.5, we get a new apparent altitude, so HA, but we've taken the 0.5 off, so it's actually 31.3 arc minutes now. But then we have yet another correction we need to make called the altitude correction. And that's actually about refraction. So atmospheric refraction is basically, as light passes through a transparent medium, the density of the medium can bend the light. It's the same thing that makes your glasses work, or say lens in a telescope or anything like that. As the light moves from one medium to a denser medium, it will bend toward the more dense medium, which allows things like lenses to focus things. But of course, our atmosphere can do the same thing. as you know, the atmosphere gets thinner as you go higher, and so as you're looking at an angle through the atmosphere, it's crossing these different layers of density, which will have a tendency to bend the light down. And so that the result of that is it causes things to look a little higher than they actually are. So we have to then counter that. Kind of like we had to counter for the dip correction. When we're looking up at our star, the star is appearing a little higher than it actually would in reality, and the amount that it changes depends on the angle, because it depends, the angle at which we're cutting through those layers of the changing density of the air affects how much refraction happens. And so of course we have another table, and we plug in our altitude angle, our apparent altitude angle, into that table, and it'll give us how much we need to subtract to pull that angle down. So in this case, we were pretty close to 55 degrees, so we're going to take out 0.7 arc minutes. And so like I was saying, refraction gets way worse as you get lower. So it's really pretty bad as you get close to the horizon. It's basically nothing when you're looking straight up, because you're cutting at, perpendicular through the gradient, so then it doesn't deflect at all.
Dad, when would you be 8 feet, your eye height? When would your eye height be 8 feet or?
It depends on how high your deck of your boat is off the water, and then how high you are. So it's like 8 feet is the number of feet from where your sextant is at your eye to the water level. So you can figure that out, of course, even before you get out on the ocean. You look at about how high your deck is off the water, and you say, oh, that's adding about 3 feet. And you say, well, up to my eye is about 5 feet. Therefore, I know my eye height is about 8 feet. So you calculate it ahead of time, and you hope you get it close, and that the waves don't throw you off too much. So we've done the dip correction. We've also subtracted our altitude correction, sometimes called the refraction correction, and that gives us our observed altitude. I don't know why they chose these particular words. I feel like when you're first looking at it, it should be the observed one, but when you get all done with your corrections, we call it the observed altitude, which in this case is 55 degrees, 30.6 arc minutes. But we're not done. That's not actually the angle we want. That's what we call our altitude angle. So you've got horizontal, we've got an angle up here, and that angle is our altitude angle, but what we really want is the angle from vertical. So we've got, this right angle here, vertical and horizontal, and we've got the star splitting that. The one we really care about is how much the star is declining from the vertical. So we subtract our altitude, our observed altitude, from 90 degrees, you get what we call the co-altitude angle. So we know how much the star is declining from vertical rather than how much it's rising from horizontal. That seems strange, but it'll be very clear in just a little bit. So we've got our co-altitude angle, and the other thing we need is that ground position of the star that we just got the angle off of. And I'm not going to get into a lot of detail, because this is a real advanced topic of how you go into the nautical almanac and get all that, but I'll talk about it really quick. You can see here's the list of stars. These are these ones from all the common constellations. They're the really bright ones. They're the navigation stars. You look up, first, so there's two columns here. You've got the SHA is what's called the sidereal hour angle, and the DEC is the declination. Declination is just latitude. You can go in this column, you can know exactly what the latitude of that star, what its ground position is. Because the stars follow these perfect east-west tracks, because the Earth is rotating, so the ground position of the star is just tracking from east to west. If you see it overhead, it's just going to be heading west. But the longitude is a little more tricky because it's changing over time. So we start out with this thing called the sidereal hour angle, is basically sort of a starting reference point of how far these stars are from, say, the meridian at a particular given point in time. There's only one time in the year where this would be the longitude. So you've got to adjust based on your date and time. And we do that with these tables over here. We've gone to the nautical almanac page for the specific date, and then we look for the specific hour. And we find the number that we add to that sidereal hour angle, and we go back into the back of the book, and we found for the number of minutes and seconds, there's some additional increments. We all get that all together, and we get something called our GHA, which is our Greenwich hour angle. And that is basically our longitude. I won't go into all the fidelity calculations, but it's basically, that's all you're doing is you're taking that column over there and you're adjusting for time. Sorry, you got a question?
Is this, I've seen there's different tables for
like the fixed bodies and the moving bodies?
Yeah, there's like, this is right here just giving you stars.
Yeah.
There's also things for planets. You have several planets like Venus and Mercury and Mars that you can also use, but they don't move on those perfect tracks. You know that they're called stars, they're wanderers, or the planets literally means wanderer. And they'll do these funny little things. So there's actually separate tables to account for where the planets are going to be. And they, basically the astronomers have calculated all those positions for you and made those separate tables. With moon, you get things like the moon is close enough, you have parallax, where it will actually have a slightly different angle based on where on the Earth you are. So you have another table that adjusts for the parallax. And so there's lots of fiddly stuff we're not going to get into in this intro class.
And that chart has 3 dates on it. So you're using the same numbers for those?
Yeah, well, what it
dates?
is, it's a truncated part of the page. So basically, it's the 3 dates, Saturday, Sunday, and Monday. Right here it says Saturday. This is just the Saturday part. If you kept scrolling down, you would find that then there's also the Sunday and Monday section that looks exactly the same, just with slightly different numbers. So that can be a little confusing the first time you look at it. You don't know like exactly how it's all laid out. So, but my point was just to say that you basically have a bunch of tables, and you can get to the latitude and longitude by looking up things in these columns and applying the time to know how you adjust the numbers. How does that get us our latitude and longitude, though? Okay. Well, if you think about this is the Earth. I know it doesn't look very exciting. I don't have any of the map of continents on it, but and we're actually at our boat is at that position right there. We're not necessarily at the North Pole. Just for purposes of making it easier to understand, I've oriented the Earth so we're right up at what looks like the top. Our zenith is the point straight above us. So we can draw a line from the very center of the Earth through the position of our boat up to the zenith. We're looking straight out at the horizontal, what we call it our celestial horizon. Fancy word for horizontal is all it really is. And we've got that dip where our visible horizon is actually slightly lower than that. It's kind of exaggerated in this image, but so that's what we're starting with when we get our angle. And then we've got some sort of star that we're looking at. So it's about 55 degrees up, but we actually want to get that, what we call the co-altitude angle. We subtract that from 90, so we're getting actually 35 is our co-altitude angle. Why is that useful for navigation? Well, the ground position of the star that we can look up in the nautical almanac just based on the time, we know that latitude and longitude coordinates. And we know that the very definition of a ground position is when you're there, the star will appear to be directly overhead. So the zenith of the star is like there's a line from the center of the Earth through the ground position of the star up to the star, and that's making an angle from the center of the Earth. Our zenith and the zenith at the ground position is making an angle, and wouldn't you know it, it's the same as the co-altitude angle. So just some nice simple geometry there. 2 parallel lines joining the same line create the same angle. Which means there's this nice little arc right over here that we can calculate based on knowing the circumference of the Earth. So that's actually why nautical miles are different than statute miles. Nautical mile is actually the distance that is set to be 1 arc minute of the full circumference of the Earth. So there's 21,600 nautical miles around the circumference of the Earth, because that's how many arc minutes there are in a full circle. 60 arc minutes times 360 degrees, 21,600. If you ever wondered why there's such a thing as nautical miles, it's just to make celestial navigation easier. And okay, so we know where the ground position is. We know how far we are from the ground position. We just still don't know where we are, but we know how far we are from the ground position. So we know we're somewhere on this circle. It's called a circle of equal altitude. So called because there's that altitude angle we can get. Anywhere on this circle, which is the same distance, that 2,100 nautical miles from the ground position, anywhere on that, we're going to get the same altitude angle as our position. So we don't know where we are yet, but we know we're somewhere on that circle. Now this diagram here, if you look at it, it might look a little bit familiar because we have this thing here. where we were looking at getting these angles to Polaris. If you take that diagram, you tilt it so the ground position is up at the top, and then like our observer position is kind of comes down here, it's sort of the same thing. We have an angle from horizontal that's going to this parallel light coming from a star, and we've got a circle that we're defined on. So basically, latitude circles are circles of equal altitude. It just happens to be the star is Polaris. It's the North Star. Technically, the North Celestial Pole, since Polaris is slightly off-center. But, and it's actually the person who figured out the modern version of celestial navigation. This was sort of the aha moment for him. Is like, you know what we do with Polaris? We can do that with any star. We just kind of have to tilt the whole thing a little bit. So, circles of equal altitude. If you can get 3 circles of equal altitude, they will intersect at your position. You don't know where you are in any one of those circles, but you know you're on that circle. So if you do more than one of them, you can find yourself by where those circles intersect. And I'm going to show you how that works with another video. So basically, we get that distance from the from the ground position. We know it's a curving arc length because Earth is curved, and I needed some sort of scale in order to know how big to set the drafting compass if I was going to draw this on a globe. But conveniently, any line of longitude or the equator is 60 nautical miles per degree. I'm going to stop just a minute so I can actually be more clear about this. But I'm doing this demo right here on this globe here. And I was using technically it's my navigation divider that I taped a dry erase marker to. What I want to do is draw these circles of equal altitude on the surface of this globe just like they are in the real world. But I need to know how big those circles are, and I know that's an arc length. How do I find that arc length? Well, I know it's 60 nautical miles per degree, which is, that's what latitude and longitude are. They're degrees. And at the equator, we know that's the circumference of the Earth. So every single degree of longitude along the equator is going to be 60 nautical miles. All I have to do is set the span of my drafting compass, like put one end of it on the 0 longitude line of the prime meridian, set the other end of it to be out to the longitude line that matches the co-altitude, and I've now set it to be the same size as that distance from the ground position to where I was as an observer. And then I can just like I would be doing it on a flat piece of paper, but instead of doing it on here, I can go ahead and draft that circle. So that's what I'm doing here. I'm going to go and start that again. So first thing I'm doing is I'm measuring out the distance for Altair. So I'm just sizing it up on the equator to get the span of my drafting compass to be the right size. I've marked out the latitude, longitude positions of the ground position for Altair is the center point, and then I'm simply drawing that line. Now, obviously, when we're out at sea, we're not doing this on a globe. We're doing charts, and get some complicated math to make that happen. There's something called intercept site reduction. But this, I think, is a really great way to kind of understand the underlying geometry that allows us to do navigation. So now I think this is probably Shedar. I have a voice commentary that would be saying, yeah, this one is Shedar. And then Saturn is the last one. So I see you can see Saturn written on there. I've got it centered on the ground position of Saturn. If the person was in Africa at that point, at the time I took that site, they would see Saturn directly overhead. But what we care about is the fact that from where I was taking these observations, that's where those lines all intersect. I recreated it on this thing here if anyone wants to look at it. And that's where I was. I don't know if you recognize that as the Wind Point Lighthouse. It's a great place because it kind of juts out into the lake a little bit. So I had a nice span of the lake horizon I could get those star sites from. And then I had a nice landmark I could verify the latitude and longitude. So now this is a very rough way of doing it. So it was like I was in with maybe a quarter to a half a degree. You can get much more accurate when you're doing it on paper. And we can do that by, like I said, there's a process called site reduction. Actually, maybe, oops, let me get out of this again.
How far off were you?
In this case, I was off by maybe about 6 nautical miles, which is actually a pretty good fix. I was kind of surprised because I was pretty rusty at that point. Like, usually if I'm under 10, I'm feeling pretty good. That's not a bad fix. Even like sometimes it's just the weather's not good, and you can get it within 20, you should be happy. I mean, if you think about it, you're out in the ocean when you're navigating, and you're traveling thousands of miles. For most of the journey, if you're keeping it within 10 nautical miles, you're pretty happy. It's when you get closer to shore, you want to kind of make sure that fix is getting pretty good, so that you're not having to track one way or the other to actually get to your port. But generally, if you're getting within 10 nautical miles of your destination, you can usually start to sight landmarks. And then get in a little closer. So let me okay. Oh yeah. So that was the Wind Point Lighthouse. Here's another kind of graphic of showing where those lines all tracked the original sites. Now, what that actually looks like I said, we wouldn't actually normally do that on a globe. We'd use something like this. This is what we call a plotting sheet. And this is a navigation divider. I've got those here. Just grab those out. In case anyone wants to look at any of these. I've got some plotting sheets in my navigation divider. And basically it has a scale on it where it's got, this is divided by latitude and longitude. But of course, longitude changes with your latitude. It's narrower as you get to the poles. So you would just kind of use this almost like a little calipers, and you line it up on the latitude that matches where you're at. And then you use that as your scale for the longitude. So you can use this particular sheet for any latitude and longitude as long as you kind of strike a line on it matching your latitude, so you know what scale is going this way. You can see it has a latitude scale in it. Latitude doesn't change. Latitude, it's always 60 nautical miles per degree of latitude, but longitude will be widest at the equator and get narrower as you get to the poles. So you have to do this adjustment. So you see this goes up to about 70 degrees. Celestial navigation is a little trickier as you get closer to the poles. There's totally different tables you have to use. Most people don't go that far. So, and what does an actual plot look like? Looks something like that. This is one I didn't use. I used a different scale on this one, so I actually used a ruler instead. Actually, you can do celestial. Let's get back to it. You can technically do a plot without these fancy plotting sheets. I've sometimes been stuck with just plain paper, and I just use a plain old, what is it? One of these. Protractor. So you can actually use this because the whole method is you're zooming in to a very much smaller part of the globe. So you're not dealing with this curving surface. As the smaller area of the globe you get, the less curvature you're dealing with. So you can get to a point where you can approximate these things as straight tangents. So something like this here is only several nautical miles, so actually only a few arc minutes of curvature. The curvature you're dealing with at this point is pretty small. So by zooming into a much smaller place, you can reduce that error you would get from the curvature. And that's why when we talked earlier about dead reckoning and your assumed position, it's a very important thing, because we're starting out with our assumed position where we think we are in the very center, and then using some math, we can come up with some lines and figure out how far away from that we were. Basically what we have here is we have something called azimuth lines. There's these little arrows that point to stars, are literally the directions to the stars that I cited. And then our circles of equal altitude will always be perpendicular to that line. And so we come up with tangents that are perpendicular and cross. And they cross up there. You can see there's like a little circle thing that's circled, and there's like a little triangle around it. That's what we call the cocked hat. That's actually our fix. That little narrow triangle that's got a circle and an X in the middle is the actual position fix, where I made that little triangle where all the lines of position that were like portions of the circle of equal altitude, they cross and make this little triangle. They don't intersect perfectly because there's always a little bit of error in the process, but we know we're somewhere in that circle, or at least we think we are. And so I kind of find the average in the middle there, and we say that's my fix. I think I'm just about there. And in this case, I was only about, like I said, I think about 6 nautical miles off from the actual position.
Dad, Is that then the difference between the set and drift?
Between what?
The set and drift, your dead reckoning and your fix?
Yeah, there's like, basically, your assumed position is just you've been traveling a particular bearing at a particular speed. You knew where you were from your last fix or from leaving your port, departure, and you made your dead reckoning guess, basically, educated guess of where you're at. You've drifted from that, maybe because your compass was a little off, currents were pushing you a little bit, or whatever. You don't know how much you were off, so you're getting this position fix where we're basing this not off of any kind of estimate, we're basing it off of the sun. But because we're starting with an assumed position, we can kind of zoom into just a limited part of the map, not have to look at the whole globe, which is why we can use some funky spherical trigonometry, basically. Now, there are formulas, like when I learned this, there's formulas for doing these calculations of azimuth angles and what we call intercept distances and some of this kind of stuff that I programmed into my HP calculator because I didn't want to lug around all the books. In the olden days, they had something called site reduction tables. And basically, it was all those calculations, all that messy trigonometry, they pre-calculated it for a degree at a time. They gave you all these different combinations of what different angles your azimuth angles might be, and they pre-calculated answers, and you literally have a stack of books. And so you flip through to the right, degree reading, and you can look up the number that you would get. Whereas, nowadays we punch it into a calculator.
Would you do this every hour?
Well, you do it every time you do a fix. And so generally, like I said, you've got...
No, your fix, do you do that every hour? Let's say you're going on an eight-hour sail.
Mm-hmm.
You go through the night without GPS, obviously.
Right.
Every hour, just to
Well,
determine?
you would try and keep your dead reckoning position up to date as you sail. So you keep a bearing for a while, and then anytime you change your bearing, you need to make a note of it. Say, I've been traveling for this bearing for this distance. I've been traveling, with the speed I think I'm doing. At this particular time, we changed our bearing, or the speed died down, and now we're traveling at a different speed, or whatever. And so you need to keep in your logbook. You keep a bunch of information to let you know what sort of track you think you've been doing. And so, of course, the longer you go, the less accurate your assumed position is going to be, which is why you want to try and get at least one or more fix in every day to try and get you back on track. Sorry, Wade.
So this is an alternative method to the one we were talking about before, where you're just taking bearings to different stars and triangulating your position.
Well,
as opposed to...
Yeah, we've talked about several versions. There's dead reckoning, which is still something you do in between celestial navigation. There's the meridian passage, where we're looking at just the sun and we're kind of getting it based on where it's overhead. Yeah. And then there's this method where we're looking at it's this is just the paper version of what I did on the globe. So this is the method where we get the distance from the ground positions, we're getting the circles of equal altitude, and we're getting that intersection. So this isn't an alternate method so much as the paper sort of refinement of this process.
Okay. You still need to know the ground positions.
You definitely need to know the ground positions. So the ground positions, what's happening, as long as we have some time, you notice over here I've got some things where it's AZ, and there's something with degrees, 146 degrees or whatever. That's an azimuth angle. That's literally these lines here where they're matching up with this sort of compass sort of thing. That's the angle to the star from the assumed position. The int is the intercept. And what that is there's a distance of our assumed position from the ground position that we can calculate using the nautical tables. And then there's the distance we measured with our sextant, where we know from the measurement of we are actually, or at least pretty close to, this actual distance based on the angle. And we've got this estimate based on our assumed position, and the difference between them gives us how far along that azimuth angle to draw the line of position. This thing, like right here, this one that's labeled Sharpitor, is literally a segment of the circle of equal altitude. If we could extend this thing on far enough, we'd have to make it start to curve. Right now, it's basically just a little perpendicular tangent to the full circle of equal altitude. But this distance here is the difference between our measured distance to the ground position and our estimated position to our assumed position. from the ground position. So that allows us to calculate what's called the intercept, the difference between our estimate and our measured distance, which allows us to then eventually make that little triangle. Sorry.
So in this example, how far is this from the dead reckoning to the actual position?
That's like I said. I think it's about 6 nautical miles. Normally I like to write it on there, but I didn't actually do it in this case. Let's see. That was my estimate there, and I think, what did we say? Somewhere back here we've got Wind Point Lighthouse is 42 degrees 46.9 compared to, I had 47.9, so I was off by a nautical mile there, and then 45.5 arc minutes compared to 41.5, so I was a little farther off on the longitude. So that kind of gives you like those. I had it not too bad actually, but that's basically it. I mean, I went a little deeper into the site reduction thing. That's actually a more advanced topic than I was gonna cover, but we had a little bit extra time, so I thought I'd talk about it a little bit.
Is that commonly your experience that you're more accurate on the latitude than the longitude?
You know what? It can depend. Yeah, it's a lot of times the thing that throws it off the most often is the weather conditions so it can vary a lot depending on which direction you're viewing the ground positions. So your direction can shift around depending on which stars you pick and which direction they are from you. So it definitely is, when you're doing the meridian passage, it's more common to get the latitude accurate than it is the longitude. The longitude would tend to be the thing that's less accurate.
So your like second slide there, is there a way to do that on the computer?
Yes, there is actually software that you plug in the sextant angles and it'll give you the answer like that. I've got a program on here, a navigation program. It's actually a fairly popular one that, okay, this one here. This is actually a very popular navigation program there we go, moving way out. And it actually has a celestial navigation plugin where you can just put in your sextant readings and it'll draw in fact, that one picture I had in there a little farther back was actually a screen cap of that, where it draws in the circle of equal altitude and gives you your position and everything.
So you're inputting your sextant readings into open CPM there.
Yeah, that's exactly.
That's giving you
exactly.
doing the math and everything.
And there's apps on your phone. I mean, to some extent, it's like, well, your phone has a GPS. Why would you have celestial navigation app on your phone? But I mean, it's actually becoming much more relevant in this day and age in that GPS can be jammed. So the military has actually reinstituted a requirement that bridge officers learn celestial navigation. And there's actually more high-tech equipment now, where instead of just using a manual sextant, they've got these digital sky-facing cameras that can snap the sky and recognize the stars and fun stuff like that. So they've actually gone back to now doing celestial navigation. And yeah, they use computers. I still love doing it on paper. So even though I could just plug it into the computer and stuff like that, I just for nostalgia's sake, I'll go out and do a paper plot.
What's your plugin name?
What's that?
What's the plugin name?
I don't remember off the top of my head, but I'm sure if you go out and look for available OpenCPN plugins, look up something like celestial navigation, I'm sure it'll pop up.
Yeah.
I've actually, as much as I love doing it on paper, I actually have some computer-based stuff I've done that I might as well show off as long as we have some time. So I've got this fun little thing here where it's saying I've got, in this case, Ekamar, Moon, and Rigel, and it gives you the actual altitude angles and the GMT time that you supposedly did it, and you can go work that, and then you can hit the show solution thing, and it'll tell you, well, this is where it actually was, see how close you got it. So it's a fun little thing. It's actually an example program I made for a library that basically does nautical almanac calculations on the fly, so you don't have to have a full nautical almanac. You can actually just look things up. Yeah?
You may have already covered this, but do you have a specific app that you recommend?
Yeah, there's like a couple. Let me look at my phone. Let me see which ones I have loaded on here.
There's one that just says nautical almanac. That's not terribly helpful. I thought I had another one here. There's a site reduction app. You know, this is the kind of thing I should give you links because the names on these aren't terribly descriptive. And there's a navigation calculator. So I've got several. There's one in particular I like because you can put in the stuff and it'll just give you the line of position. And like when we were on the Manitou, I could get sun sights, but we weren't really doing meridian passages, but we were near the coast, and that actually can still be very handy if you're near the coast but you don't know where along the coast you are. You can kind of use the coast as your second line of position. So you can just kick a sun sight, get the line of position, you know, that circle of equal altitude line of position for the sun, and see where it intersects the coast. And then you can know that, well, I'm on that line of position, so I must be just off this part of the coast. And that's actually a very, valid form of navigation. Mm-hmm.
You said three circles, right?
Right.
So if you can draw 2 circles and you know you're in,
yes.
I'm either in the Great Lakes or I'm in Florida.
Right, exactly. And then that's just called a 2-body fix. Okay. That's completely valid to do. 3 makes you a little more accurate. Okay. And there's actually a very good reason to that is you may have some sort of systemic error where every single one of your angles is reading a little bit high or a little bit low. If you can spread them out across the horizon, like have them close to the same distance apart all the way around, the errors will cancel out. So you'll end up with that little triangle. You put yourself in the center. You're going to be more accurate in the center of that triangle than in any one of the intersection points.
Right.
Oh, yeah, it's 120 degrees per is 1/3 of 360. So ideally, if you could pick 3 stars that are exactly 120 degrees apart, then if there's any systemic error where they're all reading a little bit the same, maybe because your sextant was off that day or refraction is a particular level or something, those errors cancel out. Now in the case of since I was on the shore of Lake Michigan, all mine were sort of off one direction, and that's all you can do. Sometimes you can only get 2 stars, and sometimes they're closer together than you shoot what's available. So.
Who first created these almanacs?
Some of the very first things go back as far as Ptolemy, like the actual astronomical observations kind of predate even using them for navigation. I can't remember the names of people who specifically started compiling them into nautical almanacs, but I know the British Royal Society and Naval Academy, they did a lot of that original work. The process of using circles of equal altitude was pioneered by Captain Thomas Sumner, who was here in America and was traveling, I want to say, back to Ireland, and had a day in which it was kind of cloudy. He had 1 star he was able to sight. And he says, well, I can only get 1, line with that. And he's like, but then he realized I have to be on that line somewhere. And he lined that up with a shore position, a lighthouse. But it sort of got him thinking, and it got that whole thing of like, you can treat any star site like it's Polaris. And then that means I can get these intersecting things. It's actually been refined even more. I mean, he didn't use exactly that system with the circles of altitude. He kind of started that way of thinking. And then there's Captain Saint Hilaire. Can't remember his name exactly. He's got a really long. He's a French captain. And the modern system we have now is pretty much based on his innovations on that. And I will make sure I include that in the stuff that I said. But yeah, sorry.
You made something about moon sightings?
Yes.
I'm not sure, does that work the same way?
The moon sightings are actually, in a lot of ways, very similar to doing a sun sighting because it's kind of big. The only difference between doing like a star sight is you have to account for the fact if you're measuring from the top or the bottom, and you call that the upper limb or the lower limb. Because all of the entries in the nautical almanac are based on the center of the body, and therefore something that's large enough that it's not more than just a point in the sky, you have to subtract off that half of the diameter. We call it the semi-diameter.
Why don't you just do the sextant?
Well, the problem is then you're introducing another error because are you sure you've got it right in the center? And that you might not quite. Also, there's one of the things is
refraction gets worse and worse as you get closer to the horizon. And so the sun and the moon can start to look a little squashed. And so the level of refraction changes across that vertical distance. So the center is not where you think it is. So, yeah. So,
When my son was in about 8th grade, he had to read this book called Carry On, Mr. Bowditch, and it's about Nathaniel Bowditch, who created the American Practical Navigator.
Mm.
He's a mathematic astronomer, and he developed that book that they carry on little ships. So it's a very good read.
Yeah.
Very subtle, but it's
They
very,
they still print it. It gets bigger every year probably.
the Navigator is more complicated than the actual book.
Yeah, I have a copy somewhere. I would have brought it if I could have found it. And they started out, of course, they were relatively thin, and they just kept adding to it over the years. But it covers all the theory. It covers all the sorts of techniques. It is sort of like the seminal navigation book. It's a really good one. It's the American Practical Navigator. Yeah.
How do you know, or how do you learn what stars that you should be sighting, right? It's like doing the calculations is one thing, but also like knowing
Yeah.
what stars are visible. Like how do you go about doing that? Like,
Yeah, there's a list of specific stars, the navigation stars. Like if when I had that thing up earlier of the snapshot of the nautical almanac, there's a specific list of stars. It's about 4 dozen of them, I think. I should remember the exact number.
How do you know which one is which in the stack?
Well, that's the tricky thing. There's this handy little thing. If you've ever seen these little cardboard wheels that have the constellations on them, I think the nickname for them is a Rudy, because it's a Rude astrolabe or something like that. It's the brand. That's one way you can do it. Is like you can use that to identify it. Some people just, if you're doing it long enough, you just start to recognize them. There's a few stars I can pick out. I usually know Vega when I see it. But and a lot of times it's like, okay, so a planet, you kind of that changes where they are, so you kind of have to just research that ahead of time and sort of know. There are I actually have an app I wrote as part of this thing here, which is the Star Picker, and you can put in latitude and longitude and your approximate time, and it'll say these are the stars that'll probably be visible at that time, but you still need to be able to recognize which ones they are. It does, though, give you sort of their approximate azimuth angle and compass direction and altitude, so that something like this, like a star picker, can actually help you find it. So.
The $30 sextant versus the $3,000 sextant, what is going to be in the actual, what's the difference there versus?
A $30 sextant is usually going to be a decorative piece that I'm not sure I would. First of all, it's probably not going to be terribly accurate, and I would be very careful about the sunshades on them, because you want to make sure you're not going to use something that's not giving you proper protection. I have heard some people say that they bought a cheap decorative sextant and fiddled with it and turned it into something that was somewhat usable. But I think my recommendation, if you want to get something to get started with, is go look for something like the Davis Mark 15. If you look for them used on eBay, sometimes you can find them for about $100. And sometimes you can find them for even less. Sometimes 70 or 80 or whatever. That's usually as cheap as you're going to get for something that's functional. There is actually a type of Davis one that's even cheaper. Maybe this is what you're referring to. There is a Davis one that it does not include the micrometer, and so it will not be as accurate. It will get you kind of close within a degree, but it won't get you that sub-arc minute precision.
It's like a white plastic.
Yeah. I'd forgotten that is actually an option.
Yeah. What's the difference between that Davis one and the Tamaya or the wings and black or whatever they're in?
Yeah, I did a review of these, and functionally they work the same. So for learning, this is totally fine because it works. The operation is the same. Accuracy, I think, suffers a little bit, mainly because it's made out of plastic, and the plastic will, the heat will kind of cause it to change shape a little bit, so it'll go out of calibration easier. So as long as you're diligent about calibration, that's maybe not a real big deal, but I do get the feeling that accuracy on this is not quite the same as something like the Plath Sextant or one of those other ones. This is lighter, so that's kind of a nice thing. It's like this thing can actually get kind of heavy if you've been using it for a while, and your wrist can get kind of tired. But this one is actually kind of nice that it's easy to haul around. So. Anything else? No.
Is your intent to do some of these calculations in class part 2?
Part 2 is actually going to include, we're going to go, weather allowing, we're going to go out and take some actual sun sites, and then we're actually going to plot a line of position and see how well that intersects with where we're at and that sort of thing. So, yep, that is actually something we're going to do. We're going to hopefully have enough sextants. Well, we will have enough sextants. We'll have at least 5 so that 10 people in the class that we could trade off using them. Anything else? Okay. Thank you.